Okay, so looking at the laws of probability today, we're having a go at shading these Venn diagrams. Let's see if we can do this first one. So for the first one, we've got the probability. So we're looking at the intersection of A not B. So A is this one, not B is everything that's not in B. So we need the intersection of those two spaces. That's going to be this space here. This space here is everything that's in A but isn't in B. Everything that's in A but isn't in B. Let's try this one. We need the union of A and not B. So we need everything that's in A and everything that's in not B. So everything that's in A is this. Everything that's not in B, I'm going to add this bit here. So this one's like the inverse of the one we just did.
But wouldn't the intersection count as these two? Yeah.
Yes, this isn't intersection, this is union. So if it's in A, we include it. If it's in not B, we include it. So the intersect, so what you're referring to is this section here.
Yeah.
This section here is in A.
It's also B.
But this is union, so it doesn't have to exclude things that are in not B. We have to include everything that's either in A or in not B. Okay, not A. This one's a bit easy. So A is here. This is everything that is not in A. Not A. And then A given B. So what I like to do with this one is, so I'm going to start off with graying out how the universal set is reduced. So we start by taking all of this away. So we're told with A given B, that means we're told B has occurred. What then is the probability of A occurring? So the probability of A occurring given B means this bit here. So we need to find the probability of this divided by this. So with conditional probability, I grey out. Once B, we say that B, A given B, that means B has occurred. So the rest disappears from the Venn diagram. And then we're looking at what's left of A. It's going to look like this.
So we don't
Yeah, so this one, it's the green bit, but the grey bit has sort of been removed. Yeah.
Sir, how are we expected to show that in an exam? What do we do?
I've never seen them actually ask that one in an exam. I've never seen them ask that one in an exam. We do that with a question. So I'm showing that conceptually so you have an understanding of how the Venn diagram looks. But typically an exam question would be giving you a Venn diagram to complete and then asking what is the probability of A given B. So it's about understanding space. So this is more for a conceptual visualization of what's happening. Okay, so combined probabilities. We're looking at the inclusion-exclusion principle. Has a few names, this one, the SIF principle. So the number of elements in A union B is the number of elements in A plus the number of elements in B minus the number of elements in the intersection. Why is this? Let's look at this. So the way this goes, if I want to shade A union B, if I want to shade A union B, I can shade A. So this is me shading A. This is me shading A. If I then shade B, I shade this. So this is A plus B. Now notice I shaded the intersection here in the middle twice. That's why, so what I'm doing here, what I'm doing here, if I shade A, I get that. If I shade B, I get that. I have to remove one lot of this there because I shaded it twice. That's how it works. That's how it works.
Is that how it usually is?
That's how it works. A more challenging problem is to do it for 3 sets. For 3 sets. What basically happens is if you add A, B, and C, then you have to take away the intersections between A, B, B and C, A and C, A and B, and then you have to add back in them A, B, C, what in the middle. It's a little bit hard. Okay, have a go at seeing if this law holds true for these diagrams. Let me do the first one for you. So what it's saying, we're going to do a show that question to show that it's true. So the intersection of A union B is going to have how many elements? Sorry, I think these are number of elements in each set. So number, but there's 3 in this one, there's 4 in that one, there's 5 in that one, there's 6 in this one. So how many elements are there in A union B? There are 3 plus 4 plus 5. How many is this in total? 12? So then we need to show this bit. So how many elements are in A? How many elements are in B? And how many elements are in the intersection? So in A, how many are in A? 7.
3 plus 4.
Okay, make sure you're paying attention to me and what's going on the board right now. This is the most common mistake. These two did great. They suggested that the answer was 3 and then they corrected it to 7. Why? Explain to the person next to you.
No, because I was looking at the one below it. I was looking at the wrong picture.
Get a full screen.
No, I'm trying to win.
It was a good suggestion, 3. It's very common to think this is A.
No, because I was looking at the
Okay, so A is not just this bit here. A is not just this bit here, you have to add that bit in as well. So, we have 7 elements in A. How many elements do we have in B? 9. How many elements do we have in the intersection? 4. What is 9 plus 7? 16. 16 minus 4? 12. This is how you do a show that question. A show that question requires that you don't use the information given, but you have to show that it is true. And we're showing that the number of elements in A union B will add up to 12. And if we use the formula, the number of elements in A plus in B minus the intersection, we'll also get the same answer. Do this now for these 2 diagrams here. Do this yourself now for the other 2 diagrams. Okay, take care. This is a show that question. It's a typical left-hand side to right-hand side proof. So we need to show that this equation balances. That means we have to use the left-hand side of the equation. So the left-hand side of the equation is equal to MA in union B. Use the notation. You have to copy it down. This is calculated as 13. That will be enough there. The right-hand side of the equation has to balance. The right-hand side of the equation is the number of elements in A, the number of elements in B, minus the number of elements in A intersection B. Show the equation that you're actually calculating. Show the equation that you're actually calculating. So the number of elements in A is 3. The number of elements in B is 10. And the number of elements in the intersection is 0. This will give 13. This shows that the left-hand side, you should actually end with, therefore, the left-hand side equals the right-hand side. And then we complete our proof correctly. This is the type of notation you should be doing. Watch out for the show that question. For a show that, you have to show the mathematics. You have to show how it's working. Okay, have a go at the last one. Okay. I'll go super formal. The left-hand side. What is the left-hand side of the equation we're trying to show? It's the number of elements in the union of A and B. How many elements are there in the union of A and B? 13. The right-hand side. What is the right-hand side? What is the right-hand side of the equation? Sorry, Yasmin?
Number of A plus number of B minus A.
Show what it is that you're calculating.
3 plus 10 minus 10.
Show what it is that you're calculating like that. How many elements are there in A? Nope.
13.
Yeah. A is this space here. That's A. How many elements are in there? 13. How many elements are there in B? 10. How many elements are there in the intersection of A and B? 10. The intersection of A and B is this, because remember, this is A. This gives us 13. The left-hand side is equal to the right-hand side. This is what we're trying to show. A show that question with an equation. You're trying to show either how the equation is made, or you're going to try and show that the left-hand side and the right-hand side are the same. You have to start with the left-hand side and say this is what it is, and this is how much it's worth. The right-hand side, this is what it is, this is what it's worth. And then you say the two are the same. Okay, so two events, A and B, are mutually exclusive if they cannot both occur at the same time. Knowing that A has occurred means that you cannot get B to occur. The occurrence of each event excludes the possibility of the other. This means that the intersection of the two is always 0. This means the intersection. Draw a Venn diagram showing mutually exclusive events A and B. How's this going to look? How's it going to look if there's no intersection? George, see if you understand. Yeah? Okay, so how is a Venn diagram going to look when they're mutually exclusive? We're going to get two separate circles. This is a Venn diagram. This is a Venn diagram of mutually exclusive events. Can you brainstorm an example of two events that could be mutually exclusive? You have to be more specific. You have to give more information.
IB AASL and IB AISL.
Okay, student selecting
Yes, classes.
AASL and AISL.
Or students selecting for basketball or football team.
So a student in the current setup, you can't do basketball and football in the team. Anything else? Try and give a non-school related one.
Maybe like someone can't be at the same
Millions of them.
Maybe like there's two parties and then you can't be at both at the same time. You can only go to one.
Yeah?
You can only sit on one chair.
Yeah. Your birthday this year.
Only once a year.
If it's on a Wednesday, it can't be on a Thursday.
Yeah.
This year. All right. How do we calculate the probability of A union B?
You add them up.
This is the probability of A plus the probability of B. So if we compare it to the inclusion-exclusion principle, you got the probability of A union B is A plus B minus the intersection. So obviously, if there is no intersection, it's just going to be A plus B. How do we determine the probability of A given B?
You subtract them.
No.
A zero.
There's one
Did you not say
The probability of A given B in mutually exclusive events has to be zero because they're mutually exclusive. It means you can't do one if you do the other.
for question 3, if they don't give you numbers, would you just write it like that?
Yeah. They won't ask that because it's on the formula sheet.
Okay.
All right, have a go at this question. Work together in pairs. So we need to find out how many students are taking biology. We're going to use the inclusion-exclusion principle as usual. So we've got the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. Which of these do we have? So there are 8 students take art. Which one is that? A. So that's this one. There are 2 students who take both art and biology.
Intersection.
That's the intersection. We also know that 18 students take either art or biology or both. That's the union.
Can we just put this in back on?
Yeah? Easy enough. How many does that leave for the number of elements in B?
No, what if it's
No,
It'll be 12.
we did it wrong.
12, right?
I'm getting 12. I'm getting 12. Let's have a little help us with our problem solving. Let's draw a Venn diagram for these type of problems. We'll make some of the bits and pieces easier. So A, B. How many's in the intersection? 2. How many's in the in B? 12. 8. So the Venn diagram should look like this. Is it?
Yeah, it should be 8 in A, 2 in B, and then another 8 in, sorry, 2 in A and B, and then 8 in B. Because there are 8 students who take art, 2 who take both. And then when you calculate that gives you 8 who take biology.
How many?
8 that take biology. This is art, 8 who take art only, 2 who take both. Not 6.
How many students take art?
8 only.
How many students? How many students do I have taking art?
It's saying art only, and it's take both. No, it says take art.
It doesn't say only art.
It doesn't say only.
It doesn't tell you how many students take art only.
Arts, like 8 students take art.
8 students take art. That's this green bit. There are 8 students take art. There are 2 that do both. So that green bit is correct.
But it's the other side is that
There are 12 students that we calculated that take biology. So that's 12, because there's 2 that take both. The union is 18. 10 plus 2 plus 6, 18. I've got it correct. Okay. Take a minute or two just thinking it through, because these type of things are tricky. That's why we do the practice problems. You got to do plenty of practice problems there. One of the most trickiest things is the idea that 8 students take on, making this one an 8 instead of a 6, and vice versa. There is some confusion in the language here on this one if you're not careful. So B, given that a student takes art, what is the probability that they take biology? So get used to be able to turn this into symbols. Get used to being able to turn a sentence like this into symbols, because with conditional probability, putting it up and then having the formula often gets you a point. Even if you don't get the question right. So you often see in the mark schemes that the student is given the method point for recognizing conditional probability correctly. So for this one, we have the probability. Do we want to find A or B? We want to find the probability of B given which one has occurred? A. Conditional. So B given A. This is the probability of B intersection A over the probability of A. Recognizing this and getting it entered in correct, because that's not how it is on the formula sheet, they're the other way around on the formula sheet. But recognizing conditional probability from the wording, putting it into the formula correctly, like this, and doing the substitution, because often you'll get letters that aren't A and B. But if you get the letters in the right place, that's your first point, even if you don't get it right. So what we need on this one, we need the probability of the intersection. So that's going to be 2 over 8. So a quarter. C, are events taking art and taking biology mutually exclusive? How do we answer this question? No. You have to give a reason. You're not going to get any question where you're just going to say yes or no. For this type of question, you always must supply a reason. So what would your reason? What would a suitable reasoning be? Ella. Ella. Can we get that down into a couple of words or less?
There are ones that happen at the same time, such as intersection and that was their intersection is not 0.
That's it.
Their intersection is not 0.
I would go for that. Sorry. Are we? Come on, Pass. Are we focused over here?
Yes.
Sorry, no, this podcast have been.
Okay, exam style question. Have I got the exam style question now? Last one then. Okay, so we've got 130 applicants for either the art or the science program. Some get accepted. An applicant is chosen at random from the group. Find the probability that the randomly chosen applicant was accepted. So so for A, the probability that they are accepted is going to be 17 plus 25 over 130. So that's 42 over 130. Can we simplify that? Put it into your calculator. 21 over 65. B. Sorry, are we going to look at the math or are we just going to chit chat? So for B, we need the probability for art. So for them to get accepted to art, it's going to be this row. So we need 17 plus 24 over 130. 41 over 130. C gets a little bit trickier. Two different applicants are chosen at random. Find the probability that both of them had the art program. So we need the probability of blue. We need the probability of art and then art. So that's going to be 41 over 130 multiplied by, what's the probability of picking a second candidate?
40 over 1.
Going to be 40 over 129. Put this into your calculator. What do we get? 41 over 130. 40 over 129. You get 164 over 1677. What's that as a decimal?
0.0978.
Okay, have a go at exercise 7F.